This is chapter number 13, which is kinetic theory. So we are taking question and answer on kinetic theory. Estimate the fraction of molecular volume of actual or to the actual volume occupied by oxygen gas at standard temperature and pressure. We have to take the diameter of oxygen molecule to be 3 angstrom. So the diameter of oxygen molecule is given in the question. This diameter is 3 angstrom. If we want to find out the radius, we divide it by 2. So this becomes 3 by 2, that is 1.5 angstrom. 1 angstrom is equal to 10 to the power minus 10 meter. We convert it into centimeter. Now the actual volume, we know that if we talk about 1 mole of a gas, that is actual volume occupied by 1 mole of oxygen at standard temperature and pressure will be what? 22.4 liter, that is 22400 centimeter cube. Now molecular volume will be what? This is 4 by 3 pi r cube. We are assuming it to be a sphere, proper sphere. So 4 by 3 pi r cube into n. So what is this n? This is the Avogadro number. So volume is, this molecular volume is always computed by this 4 by 3 pi r cube into how many you can say particles are there. So this is the, or you can say how many molecules are there. So n is the Avogadro number, which is this number, this molecules per mole. So when we multiply these two, we know pi, we know r, so r is taken from here, and then we know n, so this n can be taken from here. So this comes to be 8.51 centimeter cube. And now what is the ratio? Because the question is being asked about the fraction. So what is the ratio of molecular volume to the actual volume? This 8.51 divided by this 22.4 liter or 22400 centimeter cube. This gives you 3.8 into 10 to the power minus 4. Molar volume is the volume occupied by 1 mole of any ideal gas at STP, standard temperature and pressure. The standard temperature and pressure means 1 atmospheric pressure and 0 degree centigrade. So we have to show that it is 22.4 liters. So in the previous question we used and I told you that it is 22.4 liters or 22400 centimeter cube. So how has it come? The reason is the ideal gas equation, which relates the pressure, volume and absolute temperature, because these two are, this is constant and this is specific for a gas. So PV equal to nRT. Sometimes you will find in book it is written as mu also. In place of N it is mu. So what is this R? R is the universal gas constant, which is having the value 8.314. What is this N? That is the number of moles, 1. We have to find for 1 mole, so we'll take 1. The standard temperature is 273 Kelvin, that is 0 degree centigrade. We have to convert it into Kelvin. Then the pressure is 1 atmosphere. Let us convert it into the Newton per meter square. So we have to use this number. And in the previous formula, as I said, PV equal to nRT. When we want to find out the volume, take volume on one side, others on right hand side, and put all the values. This is n, this is, we know, 8.314. This temperature is also known to us, this pressure is also known to us. So this comes to be this meter cube, and you convert it into liter. This is 22.4 liters. So the molar volume for gas at standard temperature pressure is 22.4 liters. Now this figure shows a plot of this PV by T versus the P. So PV by T with pressure. So pressure is on the x-axis and PV by T is on the y-axis. So this much kg of oxygen gas at 2 different temperatures. So we have T1 also, T2 also. There are 2 temperatures. So what does the dotted line or dotted plot signify? See this when this is a straight line, that is the pressure is constant. So when we are talking about pressure being constant, this is what? This line says that the dotted line corresponds to the ideal gas behavior. See, this has to be the ideal gas behavior, which is parallel to this x-axis. So this tells you that for any value of P, this PV by T will remain constant. You know, if P pressure is changed, this PV by T should remain constant. This is the dotted line which is idealized. Now the second part is, which is true? T1 is greater than T2 or T1 is less than T2. See, in this case, for same PV by T, this T2 is less than T1. And if you see here also, after they are intersecting for the first time, this is T1 and this is T2. Again, this T1 is closer to the ideal situation. So in both the cases, this T1 is closer to the ideal situation. That is why T1 is greater than T2. So we have T1 greater than T2 because the upper position of PV by T, it shows the value is lesser for T1 and T1 is more closer to the dotted line. In this similar fashion, after this also, T1 is already always, as the previous one, is closer to the ideal behavior. Now, what is the value of PV by T when the curve meets the y-axis? So when it is going to meet y-axis, we have to find this value. How to find it? We will use the formula. We know that when PV by T is on y-axis, this P is on x-axis. We know that this PV is equal to mu RT. And mu is the number of moles. So in order to find mu, just take P and V and this R and T, all these values. So, but for computing this mu, which is actually the number of moles, we have to take these two numbers which are given to us. This is the molecular mass, this is the mass. That is small m by capital M. See, it is given in the question. This is the mass in kg, and we know that the molecular mass is also given, which is 32. See, it's 32. So we have to, this is 32 unit, and this. So we divide this so that we get number of moles. Number of moles is 1 by 32. Now, if we want to find out PV by T, because we have to find out PV by T. To take PV by T means you have to take T here, denominator, so we have to find mu into R. Multiply this with R. So this 1 by 32 is multiplied by 8.31, you get 0.26. So at this, the value where this means y-axis, where it cuts, is 0.26 joule per Kelvin. Now the next question is, if we obtain similar plots for this much, same amount of hydrogen, would we get the same value of PV by T at the point where it is going to meet the y-axis? Is it the case? If not, what mass of hydrogen yield the same value of PV by T, that is the low pressure high temperature region of this plot? The molecular mass of hydrogen will take at 2.02. So what is happening here is, it is asking that, okay, this is done for the oxygen. It will happen for hydrogen or not. So if you see the similar plot for hydrogen, we are not going to get the same value for PV by T. So this is going to meet for hydrogen, but it is not going to meet at the same position, not here, and not at 0.26. So why? Because the molecular mass of hydrogen is different from that of oxygen. They have different masses. In fact, one is 32, other is 2, if you talk about the molecular masses. So for the same value of this PV by T, the mass of hydrogen required is what? PV by T is N into R, and N into R is, N is what? M by capital M. Capital M for hydrogen is 2.02 given in the question. So M by 2.02 multiplied by this R. You have to find N is given by this, R is 8.31. So this is 0.26. Now this 0.26, this whole is 0.26. We have to find out the mass for which we get this value. So M by 2.02 into the 8.31 has to be equated with 0.26 so that we can get the mass of the hydrogen. So we get mass equal to, we take this in the denominator, this in the numerator, multiply them, this is the gram. So this is the mass for which we get exactly same value of PV by T of hydrogen as it was in oxygen. An oxygen cylinder of volume 30 liters have an initial gauge pressure of 15 atmosphere and a temperature 27 degrees centigrade. After some oxygen is withdrawn from the cylinder, the gauge pressure drops to 11 atmosphere and the temperature drops to 70 degrees centigrade. Now we have to estimate the mass of oxygen taken out of the cylinder. So the scenario is, there is a cylinder. So there is a cylinder. Now some mass has been taken out. The initial scenario is given. Once the gas has been taken out, the final scenario is given. We have to find out how much mass of the oxygen has been taken out of the cylinder. So there are certain values which are given here. So we'll start with the volume of oxygen, which is 30 liters, convert it into the meter cube. Then gauge pressure P1, which is 15 atmosphere, convert it into Pascal, because these two are given. The final also value is given, temperature, which is 27 degree. Initial 27 degree is given. So we write it like this. Universal gas constant also 8.31 is given. Now for the first one, that is before the gas was being taken out, the initial number of moles of oxygen, let us assume it to be N1. So for gas equation, we know that P1 V1 equal to N1 RT1. This is our gas equation. We have put 1 as the subscript because we want the initial condition. Now N1 will be what? Take N1 on the left hand side, others on the right hand side. All these values are known to us. Put the value, we get 18.276. Now we will come now to the scenario that this N1 is what? This mole is what? It is M1 by capital M. So this is the initial mass of the oxygen, and what is this? The molecular mass of oxygen, which is actually equal to 32. So this 18.27 will be equal to M1 by 32. So multiply this with 32, we get this M1. So we multiply these two, we get M1. So M1 is 18.276 into 32, you get 584.84. Now after means the oxygen has been taken out, means from the cylinder some oxygen has been taken out. So the pressure and temperature which it reduces. Now the volume is given as 30 liter, we convert it into meter cube. The pressure is also given after removing the gas. So this is the pressure too. Temperature is also being said 17 degrees centigrade, we convert it to Kelvin. Now let us now with the same sequence what we followed here, we'll find out the N2. So the gas equation for 2, that is P2 V2 equal to N2 RT2. N2 will be found out using all the values being told just now by me. So all these values to be taken, and 13.86 will be N2. Similarly, if N2 is known to us, M2 can be computed, multiplied by the molecular mass. So molecular mass of oxygen is 32, multiply this with 32. So you get the N, this M2. So we have M1, we have M2. So when we subtract these two, this 453.1 gram with the previous one, that is 584.84, we subtract them, we get this much of mass of oxygen has been taken out, because actually the mass of oxygen taken out of the cylinder is given by what? Initial mass of oxygen in the cylinder and minus the final mass of the oxygen in the cylinder. So we have to subtract these two and we get the oxygen being taken out from the cylinder. An air bubble of volume this much rises from the bottom of the lake. So there is a lake, so it is 40 meter, there is a bubble. So the bubble from 40 meter deep, this is the temperature 12 degrees centigrade. So 12 degrees centigrade is here, 35 degrees centigrade heat is here. To what volume does it grow? Because it has to grow in volume when it comes up, when it reaches the surface. What is at a temperature 35 degrees centigrade? So we have to find out that this 12 degree starts this at 40 centimeter deep. At 12 degree, this bubble start, it reaches up to the surface and the temperature goes to 35, and this height has been taken. Now we have to find out what is the volume being grown up, by volume which it grows. So volume of the air bubble, that is initially it is 1 centimeter cube. Let us convert it into meter cube. Then the height is also given, depth you can say h or d. So this is 40 meter and this is 40 meter. Now temperature at the depth is below, that is 12 degrees centigrade, converted into Kelvin, add 273 to it. At the surface, temperature is given as 35 degrees centigrade, add 273 to it. So the pressure on the surface of the lake is what? This is 1 atmosphere, because we know at the surface it will be only atmospheric pressure. We will convert into the Pascal, but at certain height, this h, what will be the pressure? This pressure here will be PA, this one, that is 1 atmosphere plus h rho g. Here we will h rho g, h is taken as d. So d rho g, and this is of course PA, which is 1 atmosphere. So 1 atmosphere plus d rho g, the density of water we can know, and we can take it as 10 to the power 3. G is the acceleration due to gravity, which is 9.8 meter per second square. Put all these values, we'll find out the P1. Now it is not yet over. We know there is a relationship. We know all the laws, the Charles and the Boyle's and the Reynolds law. So P1 V1 by T1 equal to P2 by V2 by T2. We have to find V2. Just take V2 on the one side, others on the right hand side. All these values we have just found out. Put this value, you get 5.263 centimeter cube, because it came in meter cube. We'll convert it into centimeter cube. So the air bubble reaches the surface. Its volume goes or increases by 5.263. It becomes 5.263 centimeter cube. Estimate the total number of air molecules, which include oxygen, nitrogen, water vapor, and other constituents. The room is of capacity 25 meter cube at a temperature 27 degrees centigrade and 1 atmosphere pressure. So what we are going to do here is, first we will write what all are given to us. Volume is given, V is 25 meter cube. Temperature of the room is 27 degrees centigrade. Add 273 to it, you get 300 Kelvin. Now what is the pressure of the room? It is given as 1 atmosphere. So 1 atmosphere can be converted to Pascal by multiplying this factor. Now for the ideal gas equation, which relates the power, the pressure and the volume and the temperature, it gives you PB equal to KB. KB is, K sub B is the Boltzmann constant, N into T. Now this KB is the Boltzmann constant, this value. Now we have to find out this N. So take N on one side, others on the other side. All these values are known to us. Just multiply them, you get 6.11 into 10 to the power 26. So the total number of air molecules of given room is this much. Estimate the average thermal energy of helium atom at room temperature, which is 27 degrees centigrade. The temperature of the surface 600 Kelvin, and the temperature of 10 million Kelvin, which is typically you will find it in the core of the star, the center of the star. So what we have to do here is we just have to use one expression, 3 by 2 kT. So K is known to us, which is Boltzmann constant. Okay, this K is known to us, and this K is the value, but only the thing is variation is temperature. So first is 27 degree, add 273 so that we get 300 Kelvin. Okay, just add 300 here. For 6000 you can just put 6000 Kelvin, and for this 10 million, which is actually 10 to the power 7 Kelvin, you get this much, 10 to the power 7. You just have to put all these, this value will remain same. We're just putting the different temperature, and these are the values in joules. 3 vessels of equal capacity have gases that has same temperature and pressure. So the first vessel contains neon, which is the monoatomic gas. Please understand, it is monoatomic. The second contains the chlorine. You will find it the chlorine as Cl2, so it is diatomic. The third contains uranium hexafluoride. This is a polyatomic one. Do the vessel contain equal number of respective molecules? Is the root mean square speed of molecules the same in the 3 cases? If not, in which case this VRMS the largest? So we have certain expression, but before we go ahead, the equal volumes of all gases under similar condition of pressure and temperature, they will contain equal number of molecules. This is in accordance with the Avogadro hypothesis. So Avogadro hypothesis says that the equal number of all gases under similar condition of pressure and temperature, they contain equal number of molecules. So the number of molecules in each case is going to be same. What about the RMS velocity? We know that this VRMS is given by under root 3 kT by m. So it is inversely proportional to under root m. So if m is higher, V will be less. If m is lower, V will be higher. So neon in this case, because it is monoatomic, it has minimum atomic mass. So with this scenario, the RMS velocity is maximum. So if you have been asked which one of this will have minimum velocity, so this polyatomic one, uranium hexafluoride, will have minimum velocity. At what temperature is the root mean square speed of an atom in an argon gas cylinder equal to the RMS speed of helium gas atom at minus 20 degrees centigrade? The atomic mass of argon is also given, helium is also given. So what we will do here is, the temperature minus 20 degree, we have to add 273 with this, plus 273, so that we get in 253 Kelvin. This is the temperature of the helium atom. Now atomic mass of argon and atomic mass of helium is given to us. We'll write it as it is. Now let this VRMS, that root mean square velocity, be the RMS speed of argon, and the subscript HE we use for helium. Now the RMS speed of argon is given by what? VRMS argon will be under root 3 RT by capital M. See, this is not K. When we use capital R, we have to use capital M. This R is what? This is the universal gas constant. This T is the temperature of the argon gas. So now the RMS speed of helium will be what? We use subscript helium, same formula. But we know in this given question that the RMS of both the gases argon and helium are same, so we just equate them, square both the sides. You can get rid of the square, that is root. 3r get cancelled, so eventually you get T and M of this Ar and T and M of He. So we have to find out the T of Ar. So take T Ar on one side, others on the right hand side. All these values are known to us. Multiply them, you get this value, and you can just convert it into Kelvin. So just 2.52 into 10 to the power 3. The temperature of the argon atom is 2.52 into 10 to the power 3 Kelvin. Estimate the mean free path and collision frequency of nitrogen molecule in a cylinder containing nitrogen at 2 atmosphere and temperature is given as 17 degrees centigrade. We have to take the radius of nitrogen molecule to be roughly 1 Armstrong, 10 to the power minus 10 meter. Compare the collision time with the time of molecules moves freely between two successive collision. See, molecular mass of N2 is given as 28 unit. So what all is given? Pressure is 2 atmosphere. We'll convert into Pascal by multiplying with this. Temperature is 17. Add 273 with it, so you get 2290. The R, which is 1 Armstrong, as I said, it is equal to 10 to the power minus 10 meter. We will write it like this. The molecular mass is 28. What is the smaller? Small m is simply, you know that the number of this, we have a value which is our number of molecules present, and if you multiply it by the molecular mass, you get the small m. So this 28 multiplied with the specific number, which is 1.66 into 10 to the power minus 27, and which is the Avogadro equivalent. So you multiply it, you get 4.65 into 10 to the power minus 26 kg. This R is also known to us, which is 8.31, which is the universal gas constant. This K is the Boltzmann constant. This is also known to us. So now all these things are known to us. We just use PV equal to RT. You want to find out the V, right? You want to find out the V. So V can be computed by taking V on one side, others on the right hand side. These all values are known to us as given here. You can find out the V as 1.189 into 10 to the power minus 2. But here the number of molecules per unit volume, how to compute this? This can be computed by this 6.023 into 10 to the power 23. We know that this is the value. This is total number of molecules present. But in what volume? This volume. So we just divide them. This by this, you get number of molecules per unit volume, which is 5.06 into 10 to the power 25 per meter cube. Now, what is the mean free path? Lambda is given by this expression. This d is what? D is 2 into r, that is diameter is equal to 2 into radius. We multiply it by 2r, right? So this is 2r square, you get lambda. Now Vrms is under root 3 RT by M. All these values R and T and M are known to us. M here we will use the 28 value, which is of the this gas. So we get Vrms. Now the collision frequency is given by this Vrms by this lambda. So we divide this by this. So we get V. And time between the successive collision, because this is the collision frequency, we know that the frequency is nothing but 1 by time period. So 1 by V. So 1 by V, we get 1 by this value. So you get time between successive collision, 2.17 into 10 to the power minus 10. And also the collision time will be, this is the D, which is actually the 2R, 2 into R, and divided by Vrms. So Vrms, we are going to use this value. So this is the collision time. A meter long narrow bore. So this is a meter long, held horizontally. Let me show you the question first. So this is the a meter long. From here to here, it's 100 centimeter horizontally. Contains a 76 centimeter long mercury. From here to here, it is 76 centimeter mercury thread, which traps a 15 centimeter column of air. From here to here, it is 15 centimeter of air. Now this is horizontal. Now it is turned to vertical direction. So what happens if the tube is held vertically with the open end at the bottom? This is open end at the bottom, so some mercury is going to fall, this is going to come down. This area means this area and this area will add up to form the air basically. So this is 15 plus 9. 15 plus 9 is 24. Now H is the pressure. So what is the pressure? This pressure which allows or which make this mercury to go down is 76 minus H, and this only pressure has to be added here. These are in equilibrium, so the same pressure has to be added here so that this air goes up. 24 plus H, 76 minus H. So when the tube is held horizontally, the mercury thread is 76 centimeter. It traps, length of air is 15 centimeter. A length of this 9 centimeter of the tube will be left at the upper end, and the pressure of air enclosed in the tube will be atmospheric pressure. We know this. Now let the area be cross section. We assume it to be 1 square centimeter. The pressure is given as 76 centimeter. Volume is given as 15 centimeter cube. It is given in the question. Okay. Now when the tube is turned vertically, so this 15 is added with 9, so we get 24. So this is filled in the say hand side in the horizontal position, which becomes the vertical position. So let this H centimeter of mercury flows out of balance the mercury pressure. So let H comes out. So the height of air column and mercury column will be, this is 24 plus H and this is 76 minus H. So the air pressure will be what? 76. Basically this H is the only pressure. If you want to compute it, it will be 76 minus of 76 minus H. So this gives H, and always the centimeter of mercury is the pressure. So H centimeter is the mercury. What is the volume 2? V2. This is equal to 24 plus H. Pressure 2 is H. So now we again assume that the temperature remain constant. So P1 V1 equal to P2 V2. This is 76. This is 15. This is H. This is 24 plus H. So this is a quadratic equation being formed. Solve it by Sridharacharya formula. You get two values H. We are not going to take this because we cannot take it as negative, because more mercury cannot flow in the tube. It is going to come out eventually. So 23.8 is the H. So this is the only pressure. So at the vertical position, 23.8 of mercury flows out. From a certain apparatus, diffusion rate of hydrogen has an average value of this one, 28.7 centimeter cube per second. The diffusion of another gas under the same condition is measured to have average rate of this one, 7.2 centimeter cube per second. We have to identify the gas. So here there is a diffusion going on. So we are going to use the Graham's law of diffusion. So we are going to employ the Graham's law of diffusion of gas. The rate of diffusion of gas is inversely proportional to the square root of molecular mass. So the rate is inversely proportional to the square root of molecular mass. So if this R1 and R2 are the rate of diffusion, two gases having molecular mass M1 and M2, the expression will be something like this. This R1 is given, this R2 is given, this M1 is given, M2 we don't know. We don't know which gas is this, but the M1 gas is known to us. Put all these values here and we just have to find out M2. This M2 is going to be 32, means it is roughly going to come as 31.78. We can just convert it, or we can round it off to 32, and 32 we know which gas it is, the molecular mass of oxygen. So the second gas is oxygen. So these were the question and answer on kinetic theory of gases. Thank you so much and take care of yourself.